All right, we've hit 10:30, so we'll go ahead and get started. As people are still jumping in here, we'll do a little bit of quick housekeeping before we get rolling. As we go through our presentation today, if you have questions for myself or Caroline on any of the information we're presenting, please use the Q&A window to enter your questions. You can find that by hovering over the menu bar, find that Q&A window pane. If you put things in the chat, Cassie is watching the chat. She'll make sure we got the questions from you guys. But that Q&A window does help make sure that we don't miss those scrolling through the chat. So please do make use of that if you do have questions. Um, topic today, we're going to be talking about some aeration control strategies, the sensors that we use to control aeration, a little bit about CDEC before we get rolling into our topic today. We are an applied research program at the University of Illinois based in Urbana-Champaign. We help buildings and communities achieve energy efficiency, save money, and become more sustainable, with an overall goal to help reduce the energy footprint of Illinois and beyond. Um, so we help facilities become more energy efficient. We provide educational materials, training webinars, publications. We do conduct research into different technologies, improved processes, things like that. And we advocate for a sustainable future for the state. A bit about our program today. The Illinois EPA Public Water Infrastructure Energy Assessment Program is our partnership with the Illinois EPA Office of Energy. So we thank them for their support of our program. But the program provides no-cost energy assessments to publicly owned and operated wastewater and water treatment plants within the state of Illinois. As part of that program, if you get an assessment through it, we do provide you with a comprehensive report listing costs of upgrades, payback periods, greenhouse gas reduction impacts, applicable incentives and funding opportunities to help fund and move forward with those projects. And as part of that program, we also bring continuing education webinars like today. We are also hosting a field day up in Warren, Illinois, showcasing a plant that's achieved some significant energy savings. They get nearly 50% reduction in energy consumption through having an assessment and implementing some of the measures in our reports. So if you can, please do come out and join us. Why might you complete an assessment? Well, if you're an older or existing plant or you've never had an assessment before, there are lots of opportunities that can be found. It can help use that report to plan for capital improvement projects, find out what's possible for your plant. Sometimes you're so ingrained in the day-to-day operations that you just fall into that groove. We can help you figure out ways to change things up and become more efficient. And we can also provide third-party support for operators' ideas. We know that you have improvement ideas. If we can quantify those in a report, you can use that to help push forward those projects with your city councils, budgetary offices, whoever it may be. What if you're a brand new plant or recently upgraded? There's always more ways to improve. There's always new technologies, new processes and procedures coming out. We try to keep a ear to the industry to figure out what is available, and we can help you find those opportunities that got left on the table, were outside the scope of a recent project, or got left on the table due to various reasons. So there's always ways to improve, even for brand new facilities. To apply for an assessment, we have an initial application you can find at our website. That is an old website. I thought I caught all those. The website is smartenergy.illinois.edu/water. If you follow that CDEC link, it should still take you there, I think, but it is smartenergy.illinois.edu/water. You'll find a link on that page to apply for our program. You just have to be located in Illinois and be publicly owned. Provide permissions for us to come out, visit your facility, walk through, document information, gather documentation such as your DMRs, your monthly operating reports, utility bill information, nameplate information for motors, things like that that we need to conduct your assessment. And then we do want you to know we shared that report with the Illinois EPA Office of Energy. It's a non-regulatory report, so if we run across anything in your plant, we're not turning you in for violations or anything like that. We're just helping you become more efficient and improve your processes. Um, Second step to that is a more in-depth data collection. We'll usually, after getting that initial application, call you on the phone, walk through a second form that gathers more information to help us prepare for the site assessment, know what we're coming out and going to see. We'll also gather utility bills at that time from you. We'll try to work with you, your city clerk, whoever has access to that information to make that as painless as possible. For wastewater treatment plants, we can pull your DMRs from central database, so we do that to make that as easy as possible for you as well. But we try to make this process smooth and easy, um, so that you can get the information as quickly as possible and with as little headache as possible. Joining me today for our discussion about aeration technologies is Caroline Robichaux from ABB. She has 15 years in the municipal water and wastewater industry, focusing on instrumentation and analytical measurement. She's been with ABB for the last 3 years, and previous to that was a systems designer for a chemical disinfection integrator. So Caroline, thank you for joining us today.
Yeah, you're welcome.
So before we get into the controls, the technologies, and ways to be more efficient, we need to know, why are we aerating? What's the purpose that we're trying to achieve? Um, the primary goal for aeration is to provide energy for microbes to break down the contaminants. Um, but as a secondary thing, we're also maintaining suspension of those solids, the contaminants, the microbes in that water, so that there's good contact between them, the oxygen they need to um, metabolize things, and the contaminants in the water. So there is an element of mixing involved as well in aeration control. Um, but that primary objective is providing that energy for microbes. Um, so just listen here, how many pounds of oxygen is typically required for BOD removal. For carbonaceous BOD, somewhere between 0.7 and 1.5 pounds of oxygen per pound of contaminant in the water. For nitrogenous BOD, you're looking about 4.6 pounds of oxygen to 5 pounds of oxygen, depending on the type of process. And if you're doing denitrification, you actually get a credit. You get some of that oxygen back as microbes are stripping that oxygen off of nitrites in the water. So you're getting nearly 3 pounds of oxygen back in that process that you're not having to provide through aeration. Um, the reason why control is so important is because if you over aerate, you're just wasting money and energy. Um, So that excess air that goes into the water that isn't used, it rises in the bubbles to the surface and just vents off to the atmosphere. You don't get the benefit of that oxygen in the water. So the ideal condition to minimize energy is to put in as much oxygen as those microbes are going to take up. Um, and that's what we're trying to achieve with some of the more advanced aeration controls that we'll talk about today, is putting in exactly what you need and no more. If you provide less, your process isn't going to be as efficient. You're not going to get full nutrient removal. If you're putting in too much, that's just waste that we can avoid. So getting into how do we measure and control aeration? Um, the most common choice is a DO sensor. It's pretty well understood metric for controlling oxygen in the water. You're essentially reading the residual of the oxygen at the end of the process or near the end of the process and going, well, I've got some left over, so there's plenty in the process for the microbes to do what they need to do. There's a couple different types of DO sensors, and Caroline will get into kind of the trade-offs, benefits between those later. But you've got electrochemical sensors where you've got a galvanic reaction of oxygen in the water um, with materials within that sensor that provides the reading for DO. And then you have optical sensors, which are becoming more prevalent, probably the most prevalent type of sensor for DO control in the industry. There's also oxidation reduction potential control. The benefit of this type of sensor is you're able to tell what type of process you're into instead of just how much residual oxygen there is. So if you have positive readings, you have aerobic water, generally you've got free oxygen present. As you start hovering around neutral for that, plus or minus 200 millivolts, now you're into where you're able to do denitrification. There's not free oxygen in the water, it's bound to nitrogen and nitrates and nitrites. and microbes are stripping that oxygen away. And then once you get into lower negative readings, now you're into an anaerobic condition where you're actually able to promote phosphorus removal, as those PAOs will prefer that anaerobic environment. So ORP is good for processes that have to either fluctuate between these different settings, like if you have an SBR or process like that, or for monitoring swing basin control, things like that, for like an A2O process or um, something where you've got an aeration basin with slug flow going through it, and you're transitioning between aerobic, anaerobic, and anoxic conditions. Um, Growing in popularity is the use of ion selective electrodes that can detect ammonia. Um, a lot of this is going into, as we've developed more advanced controls, and we'll touch a little bit more on some of the feed forward and early detection controls that are trying to predict loading coming into the plant so that they can react faster and have better control of aeration. Um, One of those things is the ammonia loading coming into the plant and using ammonia analyzers, either wet chemical analyzers or ion selective electrode detectors submerged in the water to get those readings and use those to more tightly control the aeration process. So those are the couple different options for ammonia-based controls. And there are now available also sensors that can take readings and correlate those with carbonaceous or biological oxygen demand in the water as well. Um, and so usually this is a UV absorption process, and that reading gets correlated to the content in the water. Since this isn't a direct reading of COD or BOD, it's a correlational thing. There is some initial calibration to set up these sensors and get them to work properly with your process. They're also not currently approved for, like, if you're taking your samples for reporting purposes, but they are available for process control enhancements. Some of the aeration control strategies. Again, we talked earlier about direct DO control. Most plants are familiar with it. The DO probe's using a feedback loop. Um, so you're just reading how much residual oxygen's in the water and trying to minimize that residual leaving the aeration process, which is an indication that the oxygen has been used up by the microbes for their purposes. It's a simple process control, pretty resilient sensors with optical DO probes. But the control loop does need careful tuning, as there is a bit of lag between um, the process and the DO reading. And it's an indirect indication of the process. So you can over or under aerate depending on where your DO probe is located in the process, how the process changes over time. While it's a very good control, um, there are ways to improve upon it. Direct ammonium control has been growing in popularity since ion selective ammonium probes have been developed. Um, Typically with a wet analyzer, there's a delay in control readings, so they weren't as helpful for controlling aeration processes outside of batch processing. But now that we have ion selective probes, you're getting a direct reading in the process with rapid results so that you can now update your process according to your needs. It's a direct measure of ammonium nitrate in the water that can replace a DO sensor in a control loop. Um, it's a direct measurement of your process conditions, so there's some benefit there. Um, but ammonia is a slower reaction than DO, which can lead to control instability. So a lot of times, an ammonium control process is paired with a DO sensor to either place limits on how much that DO set point can change in an ammonium control loop, or is cascaded with ammonium to change those DO set points separately. Sensor placement is also important. As Caroline will touch on later, it's difficult to calibrate effluent readings or near zero readings for ammonium control with an ion selective electrode. Um, so you want to make sure that it's placed somewhere in the process where there's going to be enough ammonium to be detectable reliably. An ammonium cascade control. You're placing these ammonium sensors near the end of the aerobic zone. Again, you're trying to target somewhere in the basin where you're going to have some amount of ammonium left, generally above 0.5 milligram per liter, is going to give you optimal control for calibration of that sensor. Um, the DO control loop is one that needs the most tuning. Relatively easy to set up this program where you're cascading into an ammonium reading into adjusting the DO set points. Again, location of that ammonium sensor for proper control is going to be important. Um, the process is reactive, so you can get occasional spikes of ammonium coming out of the process if you have large swings. Say you've got I&I flows or an industrial client that's putting a lot of ammonium into the water, or you have large seasonal changes in population, say you're at like a state park or something like that, college towns. Those things can have an impact on how well an ammonium cascade process can control. But by and large, you're going to have much better aeration control through this type of system. And then there's feed forward controls where you're actually feeding your ammonium readings into a model of the plant and predicting how the plant's going to react, and then adjusting your set points and amount of aeration available um, in your plant to meet those treatment targets. So the main limiting factor in addressing ammonium peaks is the existing mass of nitrifiers in the process. And since that factor changes slowly, just adjusting the DO set point or solids retention time through trying to do more recycle in the basin isn't going to have as fast a reaction as you need. Um, a lot of plants that are doing feed forward control are using swing aeration basins or swing zones in their aeration basins where they can increase the volume of mixed liquor that contains those nitrifiers in it, and in that way can better react to changing loads. So an example is shown here on screen where there's primary aeration basins and then there's two swing basins in the image. One's active, one's not, based on their loading requirements. So it further minimizes aeration energy by predicting needs rather than reacting to them. So you have a much faster response to what you need. It improves the overall effluent sludge quality because you're not over aerating, which can lead to poorer settling and things as you get filamentous bacteria production from that. Um, you're not missing your treatment targets due to under aeration. It's a higher complexity and cost to develop that model, place additional sensors in the process. You're often pairing this with feedback to control to perfect imperfections in the model. All models are ideal, all actual conditions are not. So there's always going to be some error between what the model predicts and what actually happens. There needs to be a way to correct back to actual process conditions. Um, and effectiveness can be limited by the plant's capabilities. You need to have some ability to have swing zones in your process for this to be very effective. Otherwise, you're going to still have some fluctuation in effluent ammonia where you get occasional breakthroughs with spikes coming in the influent. One of the newer things that's available now with the COD-BOD ion selective sensors is the ability to do a similar process as with ammonium, but you're doing it with direct sensing of BOD and COD. So similar process, similar benefits. Again, you're getting the ability to do either feed forward control or better cascade control of aeration with the direct measurement of contaminants in the water that you're treating for, instead of just the DO reading, which is an indirect measurement of the process characteristics. It's a little bit simpler modeling when you're using a direct measurement, but it is a newer technology, so there is some training involved, testing. People are still working out case studies on implementing this type of technology with these sensors. Um, so that brings me to the end of my presentation. I will provide control to Caroline, and she can get into more detail about the sensors themselves.
Let me see if it's working. No.
You should be able to click on the screen. I see you moving the mouse.
Okay. It's
There you
not, it's
go.
letting me advance. Okay. All right. So I have no idea why I'm nervous today. I present is basically my job, but if you hear my voice cracking, I apologize. For some reason, today is a nervous day. Seems to happen every once in a while. So I wanted to kind of cover some more of just the installation guidelines, some of the maintenance that you're going to have around these different systems that you can use for aeration control. I can also answer questions in regards to, mostly what Sean talked about already, but if you do need to know maybe how would you set up that feed forward feedback control in a SCADA and what that would look like. So first, let's start off with some probes. Installation, these are going to be put in the process, right? So we are able to do that with the ISE probes, the DO probes. See, there I go. BOD and COD, and then the ORP. Now, I'm not really going to cover ORP probes in here just because we're not actually using them that much for aeration anymore. But they can indicate when you don't have any air in the process, which is where they're useful for. So starting with dip poles, as you can see in that picture, this is a probe installed on a dip pole. That's actually not a picture, that's a rendering that we did. I don't know why I didn't put a real picture in there. The dip pole is going to be mounted to a handrail most typically. You can do like a chain mount as well. What you're going to want to do is have hardware that's easy to remove. These probes can be cleaned sometimes every 2 days, sometimes every couple of weeks. I do have some plants that I've seen last 3 months without having to be cleaned. But you do want to have the ability to remove that probe fairly easily from the process, and ideally with only one person having to do it. These dip poles can be very long, right? Generally, we're seeing like 8 feet, but I've seen some as long as 16 feet. That's on a very, very deep basin. So as I said, you're going to need to be able to remove it fairly easily. Some of those accessories for removing the probe actually can do a tilt and swivel where they can swing over the sidewalk, where you're walking upon. So that would make it even easier to remove. So talking about cabling though, all manufacturers provide probes that you can remove the cable right at the sensor tip. If you're in process, you do not want that cabling. You're going to want to have integral cabling where the cabling is potted inside the sensor. That allows, that allows for the sensor not to have water ingress. If you do have water ingress at the end of that probe where the cable is, you're going to damage not only the probe, but the cable as well. So as I mentioned, you're going to want integral cabling running all the way from the end of the probe to the controller that it's going back to. You do not want to install these without a dip pole. If you put them even on a chain and they're swinging loose inside the basin, you will see them get damaged by the sidewalls, right? That aeration is a very moving process. So we don't want these probes just kind of hanging out and swinging around in there. Another installation guideline, depending on, kind of what cost you have for putting in one of these systems, is going to be an optional cleaning system. So what that is an air compressor that is connected to a piece of polyethylene tubing that runs down to the end of the sensor. The air compressor is controlled by the controller. There's a set timer that you can put in there, and it'll activate a relay, which will turn on the compressor, and that'll blast air across the end of the probe face itself. So that is going to reduce manual cleanings where you have to physically go in and remove the probe from process. Some plants are doing this over water. I don't know why you would want to add more water to the process. It can be useful in other parts of the facility, say like at influent or even effluent, where you might have non-potable water to be able to recirculate right there. But for aeration, it's mostly recommended that you're going to use just an air compressor. So the difference there is going to be air compressor, less manual labor for cleaning, or having to remove it from the process more often for cleaning. So kind of OpEx versus CapEx there. I think I covered everything on that slide. This slide has a lot less words and pretty pictures. So when it comes to installing dissolved oxygen or ammonia ISC probes in situ, obviously we need to look at how a facility is designed. Not to rag on any engineers, but I don't know why we have to reinvent the wheel every time we create a new wastewater plant, but it sure feels like we do. So depending on retention time, physical layout, oxygen consumption is going to kind of determine some of the installation locations that you'll have. So I don't know if in Illinois y'all call it the racetrack of poo. That is the common terminology down here in Texas. So specific to dissolved oxygen probes, right, we're going to need to look at the mixing time. If you're putting that probe right where the influent comes into an aeration basin, then you're not going to see any real readings of the DO probe as it goes down the process because you don't have enough mixing time. If you want to indicate a very low level of DO, then yes, you can put in a sensor at that location. So also proximity to aerators, right? I know we've got a lot of the dissolved oxygen aerators off the bottom, very spread out, very consistently throughout the process. That's great. But if you don't have that type, say you have a floating aerator that's kind of just right in the middle, and then another one further away, we're not going to want to put that sensor right below that aerator. That just seems like common sense, right? But I have seen it done in real life before. So reaction time also, if you're too close to the outlet, you're probably not catching or capturing what's happening along the way. You also, the delay in changes, you want to look out for that. You need to make that timely adjustment. As Sean was saying, these can be very slow reacting. You'll see that dissolved oxygen level going up and down on the controller all the time. But as far as the entire process and being able to control it automatically, you're going to want to be able to make those timely adjustments. So for DO probes and their placement, generally we see this being put in as a once and done. This is where the DO is going to be installed and this is where it's going to be installed at. That is actually not the correct way to do things. And it does take some experimenting. It does take some effort on whoever's installing it, whether that be y'all or an integrator. You're going to want to experiment with that control schematic and see where the installation location is best for your facility. So being flexible, being able to move them around is for the best. Now, a lot of these sensors do have fairly long cabling. I would say the standard cable length is 30 feet. So if you have an 8-foot dip pull, you have plenty of room without moving the controller that's mounted on the handrail. You have plenty of room to kind of move up and down that DO sensor before you have to physically move the controller and the electrical work itself. And so that goes right into the adaptability is give yourself some time. Don't stress if it's going to be not quite right at startup. So installation locations for ammonia sensors. This is talking specifically around ISC sensors. So at the inlet location, you can have some problems fine tuning there, right? Same with the outlet location. ISC sensors are typically 0 to 1,000 ppm, 0 to 2,000 ppm. They do not react well at 0.5 milligrams a liter or below. So at the end of the aeration basin, at the outlet, you're never going to want to install an ISC sensor there. Now, a wet chemistry analyzer, I think I'm going to talk about in here. If not, I'll just verbally talk about it next. Those can read the very low levels and they can read them very accurately. However, maintenance is extensive on a wet chemistry analyzer. Let me see what else I put in here. So again, just like DO, optimal placement is going to be midway in the basin. Again, with experimenting in your particular facility and what that looks like, being able to move it around. Again, cable lengths sufficient in order to be able to move just the probe without moving the controller. If you have to move the controller, you have to move your, whatever communications wiring you have, whether that be Ethernet of 4 to 20 milliamp. You have to move your power. So we don't want to have to do that. So plenty of cable length may seem like what you don't want, but it can actually help you out initially. I don't believe I wrote it in one of these slides, so I just want to talk real quick about that control schematic. If you have one sensor, say a dissolved oxygen sensor, what happens when it becomes very dirty is it actually starts reading down to 0 ppm. If you are automatically controlling your blowers based off of that DO or ISC measurement, and you have one sensor that fails, your blower is going to, ramp all the way up. You're going to full blow oxygen, and then you're defeating your purpose of energy savings. Of course, you can set an alarm in there to say, hey, my sensor is reading below, a 1 milligram a liter. I know that I'm not that low. I'll go clean it. Here's my alarm telling me to get somebody out there, maintenance, whatnot, to go out and clean that sensor. What I actually recommend is that you install more than one sensor, actually 3 sensors, kind of in a similar area so you can get a full profile of what's going on there. But when you set your control schematic in SCADA, you are going to not average all 3 measurements. So if you have a 1.5, a 1.5, and a 0, your average is, oh man, math right now. What is that, a 0.75 or something? Oh my gosh, I don't know. Sorry. Your blowers are going to react and you're going to have more air just because it's averaging those 3 sensors. So as far as the control schematic, you're going to want to say, hey, if I've got 2 within 1.5 and then one that drops out to 0, ignore that third probe. Don't average. I hope that makes sense. It does make, as Sean was mentioning earlier, a little bit more trickier controls, but that's the whole idea of energy savings, is it does take a little bit to figure out. Okay, we talked about, well, Sean mentioned electrochemical dissolved oxygen probes and optical dissolved oxygen probes. Electrochemical probes are, it's kind of tricky. They haven't been used probably for over a decade, and then now they're coming back. So I'll have to do more research into why they're coming back again and why we're starting to see them again. Optical probes, that's going to be your luminescent dissolved oxygen. That is an industry standard methodology. Every manufacturer is doing it the same. Technology is great, it's solid, and it works out well for 99% of the applications. The only application I've seen where an optical probe didn't work was because they had grit in the aeration basin. I think their plant had other problems. I don't know how the grit gets there. It would actually rip up the sensor, the membranes. So as far as calibration goes, on the optical sensors, the calibration data is stored in the cap itself. I could have showed you one. The cap itself has a chip inside it that communicates to the controller. So that is the replaceable consumable part, is the membrane cap. As you're replacing that membrane cap, you put a new one in, the controller automatically knows that you have a new cap installed, and the calibration is stored there. One of the advantages to that is you can actually have a separate controller in the lab. You could do this for pH probes nowadays too. You can do any calibrations or verifications in the lab. You can remove that probe from process, take it to the lab, clean it up, calibrate it or verify it, and then you can kind of alternate it out with another probe. So what does that give you? It gives you more steady, consistent calibrations. Instead of having multiple people doing these process calibrations, you can have one person. Electrochemical probes do tend to drift. They're not as accurate. That's why the industry went to optical, more frequent calibrations. The membrane caps themselves for optical probes are more durable. They don't get ripped through. It's actually the membrane tip itself that's getting ripped through over time or degrading. So lifetime, again, electrochemical is less than an optical sensor. Replacement frequency, the DO sensor cap on luminescent dissolved oxygen or optical probes is typically 12 to 24 months. I do have facilities that only last 3 months. And I have facilities where it's exceeded 24 months. As I mentioned, the cap is consumable. And then cost, right? The optical is cheaper. The electrochemical is cheaper and the optical is more expensive. Okay, so now I wanted to talk about extractive sampling versus a probe in the process. This is where you're going to see those ion selective electrodes versus a wet chemistry analyzer for ammonia. You're going to start seeing this more and more often for nitrite analyzers as well. Wet chemistry analyzers, should have put a picture, I'm sure most of you are familiar with them. Bring the sample, you got to pump it out of the basin, you've got to filter it, and you've got to bring it to an analyzer. Wet chemistry analyzers are very accurate. They are going to be your most accurate analysis for online measurement. However, the maintenance is exceptionally high. So a lot of them can do self-calibrations nowadays. They will have buffers in the analyzer itself and standards to be able to do self-calibrations. There's a timer inside there. You can set it up to calibrate weekly, monthly. A lot of them are settable at different intervals. The OPEX on them is more, I apologize, both the OPEX and the CAPEX is higher due to chemical reagent changes as well as maintenance. And then an in-process analyzer, though, as Sean mentioned, and I mentioned before, say if you're looking at an ammonia measurement, you are not able to read below a 0.5 ppm, where wet chemistry analyzer can all day long. The probes for ISE, the tip of that probe is glass. The measuring is done at the glass. So damage can happen. Typically, a probe will last about a year before replacement. You know when to replace by it not calibrating anymore. Or if you see a lot of this going on, that's swimming, right? So if you are no longer able to maintain an accurate measurement, then that probe needs to be replaced. Probes are considered consumable for ion selective electrodes. Manual calibrations, right? You're removing that probe from the process. Let's see if I didn't cover anything on there. Again, ion selective electrodes, just like DO, you are going to have to do manual cleaning. You can do an air blast, air compressor to help keep it clean over a longer time before you have to do a manual clean. And then Sean mentioned BOD and COD. Sean, this picture is old, by the way. We changed it up. So this is a correlation measurement. What you do is you take 10 samples over the course of a week as the preferred method, and you monitor those samples in order to calibrate or create a correlation curve for the online sensor. These also come in the process like you see on the picture there, or they can be extractive sampling with a clean system as well. This one is showing you actually the air blast cleaner that's going to go down to the sensor face. So as Sean mentioned, these are not reportable probes. They are correlation to measurement. They are pretty accurate. You just need to create a site-specific correlation curve. Obviously, all of you know that this is against a 5-day test or a 3-hour test, depending upon measurement. So this can be very useful, helpful. We will start seeing this used a lot more in the industry. It currently is pretty new. So if anybody wants to be a test facility, I've got a lot of manufacturers that would love to give you an option. Let's see if I missed anything there. Your cleanliness is going to be the same, right, as all the other in situ processes. Yay. Am I done? Is that it?
That was all the slides you gave me.
Okay. Was there anything I didn't cover that you think I need to?
Let's see what questions have come in, and we'll go from there. I keep trying to scroll, and it keeps clicking on the background image. Let's see what we have.
It says I am still in control. Do I need to do something here? We use Teams. I am not used to Zoom.
Nope, got that taken care of.
Okay.
I think one of the questions for plants, especially if they're implementing controls for the first time, the actual placement of the sensor, how do they best determine where that's going to go? What are they looking for in their readings to make sure that they've got it optimally placed?
Yeah, right. So most facilities, you're wanting to control that aeration. You're wanting to maintain normally for a dissolved oxygen sensor, say above 0.8, but typically you're going to want to see a 1, 1.5 to a 2. You're going to want it. An easy way to test for this is with a hand test. But again, if you're using it in a control schematic and you want to actually control your blowers and you want to see that real life ramp up, ramp down, you do need to just go ahead and put a sensor in with a controller. As I mentioned, you have 30 feet of cable typically, and go ahead and move that sensor until you start seeing your control scheme react in a way that you want it to. I don't know that that was a very good or clear answer. My
No,
apologies
no, it makes
there.
sense.
Okay.
We did have a question come in. Are there control boxes available with the programming set up, or
There,
is there always some
oh,
field work?
controllers, yeah. I don't want to make this sound bad. Controllers are so easy to set up nowadays. Almost all manufacturers make them with an easy setup. It's like a menu, just like on open channel effluent flow meters. If you're using a simple one, you're just going to walk through a wizard that says, hey, set it up. This is BOD. Do I want to read in ppm, percent, or milligrams a liter? Do I what do I want to call this sensor? Aeration basin number 1, things like that. So they are very easy to program nowadays for the most part. It's really going to be the control side of SCADA that'll be a little bit more complicated.
Do you have a question about, do we install probes for all analytes or just one for aeration control? Like, do you want to combine BOD and COD with ammonia for better control, or uh, what's kind of the optimal pairings of sensors?
Sure. Yeah. So bare bones basics, you're going to start with your dissolved oxygen sensors if you don't have any in process. If you're wanting to fine tune the controls even more, then you can start throwing in BOD sensors. You can start adding your ammonia sensors. It just, again, as to Sean's mentioning in his portion of this meeting, is different control scenarios and how much you want to fine tune it. Your ammonia control is going to give you better control overall. However, dissolved oxygen is going to give you the simplest control. I hope that clarifies that a little bit. And then
Mhm.
using both is great.
Yeah, and actually, for a lot of the assessments we do, it depends on the plant. Like a small plant that has a limited budget, they're probably going to go with a simpler control, like a single or a couple of DO probes, and just control using DO. For a larger, more complex plant, or a plant that's really narrowing in on nutrient removal processes, focusing on minimizing their um, total nitrogen effluent and phosphorus, then you're going to start implementing other controls to better control your process and make sure that you're not going to have upsets and things like that.
Yeah. And sometimes, as Sean mentioned, a great place for wet chemistry ammonia analyzer is actually going to be at your effluent. That can kind of help you determine upstream what's happening, right?
I had a question here about feedback versus feed forward. Typically, feedback's preferred to feed forward due to greater accuracy. But do you have experience with facilities that implement feedback versus feed forward?
Is that a question for you, Sean?
Uh,
In Illinois, let me
it
take
does
that
say
one.
in Illinois.
Yeah,
Um,
I'm a
I
little
have I've
Texas.
been to a couple of plants that have the feed forward process, and they do use it effectively. I think Wheaton is one. It's actually where the example image of the swing basins came from. So they do use that feed forward predictive model to adjust. If they've got a large ammonia load coming in, they're going to need more massive nitrifiers. So they adjust how many swing zones they have active to increase that volume of nitrifiers quickly. Because otherwise, you're relying on a very long delayed process for them to grow in proportion to the other microbes in the process through a change in DO or a change in solids retention time. Where if you can just change the volume of mixed liquor overall, um, you can better adapt to rapid changes in loadings. So Wheaton's the only one I'm aware of that I know has used feed forward. I'm not sure if they're still using it or if they've adapted to a new process, because that was something that was, well, that was a number of years ago, 5, 6 or more years ago, that we ran across that at their facility. Um, the grand majority of plants I see are doing some version of feedback control, or a cascade control with ammonia into a DO controller, where that ammonia is sending a change in the DO set points, um, and then the DO controller is making sure the process is controlled based on a feedback loop.
And we are more from an instrumentation side. We are starting to see a lot of use with thermal mass flow meters to actually verify that the right? Because your blowers may be performing sometimes differently depending on temperature, conditions of that day, age of the blowers. So a lot of our facilities are starting to use thermal mass measurements of the
Hmm.
air itself.
Question about testing against a portable DO for calibration purposes. Should that portable be calibrated alongside a sample using the Winkler method if possible? I'm assuming that's for you because I do not know that process.
So calibrations and verifications are very, we've got two words there that are very different words. DO sensors need to be verified. You're going to do this by placing it in a water saturated air sample. So typically a sensor, when you purchase it from a manufacturer, is going to come with some type of vial. There will be a sponge at the bottom. You're going to soak that sponge. The sensor needs to be placed inside and sealed. You should go up to about 9.8 ppm. That is how you verify a sensor. Some manufacturers do allow you to make a calibration shift in their controller. You shouldn't really have to. You are going to want to do that with a handheld. The biggest thing that occurs with a handheld is as that DO sensor is just sitting on a shelf in between uses, even if it's a day, you need to go ahead and saturate that probe by using this method for 30 minutes before you try to compare it to an online analyzer. So the best way that we do compare with an online handheld versus an online is actually throw that handheld sensor right next to the DO probe in the process and check your measurement there. Verify them that way instead of pulling both probes out of the process. Or you can do both instances. So just kind of a terminology shift there, verification versus calibration is a little tricky. Some words that get a little mixed up in our industry.
Mhm. We did have another question about the proper depth to submerge
All right.
sensors in the flow.
Mm-hmm. Yep. Let's do the move the sensor around till we like it answer. That's my new favorite phrase. Is move the sensor around till you're happy. Actually, we normally start with about 2 feet into the basin. But like a 16-foot basin is pretty common, 2 feet submerged. And that's going to depend on what type of aeration you're using.
I do know, in particular, that question came from a plant that has horizontal rotors on an oxidation ditch, the poo racetrack.
Racetrack of poo.
Yes. Um, so obviously you're going to want to place a little bit away from the horizontal rotors because you're getting large injection of oxygen right there,
Mm-hmm.
and it doesn't have time to mix down into the depths of the basin until it's farther downstream away from that rotor. Um, so on top of uh, in that particular process, you're kind of going to have a diagonal dissipation of oxygen away from that rotor from the surface down to the basin. Do you have a preference for those situations on a particular depth and distance from the rotor?
Yes. So that one's actually where you could do a measurement. The first DO probe may not be as deep. And then the second DO probe, as you go further down, can go deeper. And then you can kind of compare and see if you are trickling down in that right oxygen that you're going to want to see.
Yeah, mixing down, diffusing through the whole
Yeah.
column. Yeah.
Yeah.
Okay.
Or you can, do one sensor further down.
Some of the early things we ran across, particularly with ammonium ion selective electrodes, was difficulty in calibration. Um, some of those were middle of basin processes. Have you run across situations where maybe their loading just wasn't enough? They'd already denitrified at that, or nitrified, I guess, to remove the ammonium at that point. They just needed to move the sensors earlier, or was there some other consideration that needed to take place?
The largest consideration with calibration of an ISE probe, right? ISE probes are pH probes in a way. The biggest consideration is that over time, as you are calibrating, each time you do a calibration, it is going to show you on the controller your slope and your offset. ISE probes are consumable. Over time, you just have to replace them. as you're monitoring that slope and offset come down, so you're going to start at 99%, right? As you're monitoring that value come down, about 80% is where you're going to replace that ISC probe. If it gives you a good indication as well as, hey, do you have shelf stock available for replacement? So monitoring your slope, your offset, which will be shown on any controller, will just help you know, hey, this probe's fixing to go down. If you have erratic values and it's not settling during calibration, that's kind of another indication of, your glass may be cracked. Your reference electrode that's inside there may be contaminated because that is part of the consumable. It's not just that the glass is cracked. You can actually have corrosion or oxidation on the reference electrode that's in the sensor itself. And normally
Mhm.
you're calibrating, say, against a 1 and a 4 ppm standard. Never do a 1-point calibration ever. That you're not going to have a slope and an offset if you do a 1-point calibration. So monitor your calibrations, keep a log of the sensor offset and slope over time as you do calibrations, whatever your SOP is. If it's weekly, if it's monthly, you may need to increase calibration if you're starting to see more common drifts. Ew.
Okay. And then as a final question, you made the comment earlier about the COD, BOD sensors being relatively new to the industry. Is there a way to get involved in testing of those probes? Um, how would
Absolutely.
people do that?
Yep. Absolutely. So what all manufacturers do is we don't like the term trial, right? You're not trying anything. It's called a delay billing PO. Most manufacturers will give you this option, and then we do ask we're going to need a case study afterwards. We're going to need a performance report on how it worked. But it's basically, hey, we're going to give you the sensor. We're going to see how well it works in the process, how it's controlling the process. We need a lot of data built around that during the trial. If it doesn't work, you don't get billed, you just ship it back. If it works, if it's helping the performance of the facility, if it's giving you real data that you do need and is useful, then you get a bill. Does that make
Okay.
sense? But yeah, anybody can reach out to me as far as any of that goes.
How much savings do you see when implementing proper sensors and analyzers and the blowers are optimized as best as possible? What's what's the control savings kind of isolating away from blower upgrades?
Yeah, you're going to see roughly between 35 and 60. That's a terrible answer, but that's what you get. That's my answer.
It
So
depends a lot on what your existing control process is. If you have
yeah,
existing controls, your savings are going to be less. If you've got completely manual control, your savings are going to be a lot more.
yeah, that's actually a great question for you, not me.
I've seen a range. Most of the reports we find are fairly conservative. They'll say somewhere around 30% savings from just a controls upgrade, um, somewhere between 10 and 30%. 10 being if you've already got pretty well set up DO controls, you're already doing some nutrient removal with that. Um, and then as far as um, if you've got more manual control, timer-based control, then you're seeing closer to that 30% range as far as the overall operating budget. Um,
And then I'm sure, Sean, that you've seen a lot of older facilities where you just have one common air header and then you're
mhm,
manually closing valves just a little bit and just a little bit, right? You're not really going to see the savings there.
yeah, yeah.
Until you put in actuators or separate headers.
As far as an annual dollar amount, it's going to vary from facility to facility. If you're really, really curious, sign up for one of our assessments and we'll try to work out a number for you. But I believe that's all the questions that have come into the chat, unless there's anything you want to address here at the end.
No, thank you all for having me. I'll come and start up or be part of one of these assessments. Just in Illinois, not in winter time.
Well, thank you for joining us today. Thank you for your insights. It's greatly appreciated. Thank you, everybody, for joining us today. If you do have any further questions, please do reach out. And also, if you can make it to that field day up in Warren, I know it's way up there on the border with Wisconsin. It's far away for a lot of you. It will be a very enlightening field day where someone implemented more advanced controls and is seeing almost 50% reduction in their annual costs. So
Wow.
thank you all for joining us today. Hope you have a wonderful afternoon. We'll see you at the next event.